Hi, I'm Melissa Ann Pfeffer. I'm an atmospheric volcanologist. I work at the Icelandic Met Office, and in this video we're going to talk about making drone multigas measurements in a volcanic plume. What I'm going to show you now is how to use the Ratio Calc software in order to process the multigas data that we collected by drone. So the last data set that we've collected was the 10th of July. That's when the drone crashed. And so this is the last measurement we have from this. So what I've done is I have opened up the file, and then what I've done is I've chosen two of the species that I'm interested in. I'm interested in CO2 and I'm interested in SO2. And what we can see here is that CO2 is the white line, and it's using this axis, so it's going up and over 3000 ppm. And the SO2 is the red line, and the red lines are going up to 300 in ppm. So this region where we have the highest values, it's oversaturated. We can't use that. So we need to look at a weaker part of the measurement. So these arrows move you over to, so what you see in the left screen is the entire time series of the measurement, and what you see in the right screen is just what's contained within these two vertical lines. And so what I'm going to do is I'm actually going to change the axis here to make it easier. So I'm going to change this to 1850. And we don't want to look at this area where it's such high value, so I'm going to move this to 2200. Okay, so now we've got the region higher up. The reason that it's in blue is because this is a region where I've already calculated a good ratio. So what we do is once we found an area where it looks like the CO2 and the SO2 are fitting together quite well, we can see in this region. And what do you see in this timestamp? You want the timestamp here. So we're going from 1851.45 to 1854.09. You want to make this as long as you can while still having a good relationship between the two gases that you're comparing. So then I look over here in this section and I look at, here's the ratio and here's the R squared. We want the R squared to be as high as possible while the time is as long as possible. So oftentimes if you just take a very, very short time window, you can get a very high R squared valued, but this isn't necessarily representative of what's actually taking place in the plume. So it's a balance between the two. And what we can see is that the white line, which is the CO2, it could use some smoothing. It looks quite ragged. So let's see what happens as we apply a filter to it. So you see how this line is becoming smoother as we apply the filter. And you can see that the R squared valued is also going up. There's a different amount of time between when the gas reaches one sensor and reaches the next sensor because the sensors are in line with each other. The pump is pulling the gases through the instrument, but there is a time lag between when the gases reach one and when they reach the other. And also the electrochemical sensors, such as the H2S and the SO2, they also take some time for the gas to be reflected in the voltage that is being transmitted through the sensor. So we very often have to shift these curves so that they lay on top of each other. So you can see that moving it this way makes it worse, but as we move it this way, it looks better and better and better. And as it looks better, the R squared valued is going up. So what we're seeing here is we've got a maximum here when we shift it 3. So then we go over to this and we see if we need to apply a filter and what happens if we do, and the R squared valued is going up. And now we can see that this looks great. This looks very nice. It has a CO2 to SO2 ratio of 2.4. Is it 2? Yep, 2.4. And we have a very high R squared value. It's more than 3 minutes, and we can see that it looks very good. So we believe this. Like, this looks like a very nice CO2 to SO2 ratio. And so we do this for the different gases, and so we have water and H2S, and we repeat the same procedure in order to populate the database of the composition of the gases that are being released during the eruption. What we have here is how I organize the measurements, the multigas measurements. So we have the name of the file, the date, then the time start and the time end. So this is those two vertical lines that I was showing you, the start and the end. then we have the maximum of the gases that we measure. So the maximum of the CO2, maximum water, maximum H2S, maximum hydrogen if the multigas has hydrogen sensor, which this drone multigas does not, and the maximum of the SO2. And then here, if we were able to get good ratios, then here is where we put the ratios. So this is the measurement that we were just looking at from the 10th of July. Here's the H2O to CO2 ratio. We record the ratio, the R² value, and the error. And we do this for all the different ratios that we're able to see. So we have not measured for anything that involves hydrogen because we're not measuring hydrogen. And then we would use ND for if a particular ratio is not detected during a particular measurement. This is how we organize the multigas measurements, both if it's measured by drone or on the ground, in order to have a good organization of the data. What I'm going to show you now is a very useful way of displaying the data. There's two main reasons why we're interested in making the multi-gas measurements of the eruption cloud. One is so that we can get the ratio of other gases to SO2. So for example, so we can calculate how much CO2 is being emitted during the eruption. And a second reason is we want to know if the composition of the gases is changing over the course of the eruption. And one of the most useful ways of displaying this data is in a triangle plot. So we use the ratios that we measured in the multi-gas data, the CO2 to water, the SO2 to water, and the SO2 to CO2. So we use all these ratios in order to plot on this triangle plot. The red dot is the petrological composition, and the yellow dots are all the multi-gas measurements we've made during the eruption. And the large yellow dot is the 10th of July data point. And what we can see is that there is some variance in the composition of the gases, but we're not seeing any systematic trend in a change in the gas composition over the course of the eruption. So for the sake of what the multigas is seeing, we believe that the composition of the gases has not significantly changed over the course of the eruption, even though we know from the petrological data that the magma itself has changed over the course of the eruption, but not within a range that's going to change the gases that we measure at the surface. In summary, what we've gone over is how to make multi-gas measurements by drone, the heartache when you lose a drone, how to process the multi-gas measurements, and how to plot them in a way that's beneficial for understanding if the eruption has changed over time. If you're interested in learning more about multi-gas measurements, I recommend you check out the following sources.